Think about the sheer effort it took to build something like the Transcontinental Railroad through the Sierra Nevada.
Oh, absolutely.
You had people directly confronting solid rock day in and day out.
Yeah.
Blasting, drilling, just tough work.
They must have gained a very visceral understanding of rock, right?
Yeah.
Through sheer hard labor.
Exactly. And, whether it's the buildings around us or the landscapes we hike through, we all interact with rock constantly.
We do. It's everywhere.
It really makes you wonder, fundamentally, what is this stuff we call rock?
That's a fantastic point, and it brings us right to the heart of our discussion today.
Yeah.
In this deep dive, we're zeroing in on the geological definition of a rock. We're drawing from some really foundational material here.
Yeah.
And our goal isn't just, rattling off definitions. It's about really appreciating the very building blocks of our planet and how geologists actually unlock the stories hidden inside them.
Perfect. So our mission today is to get crystal clear on what geologists mean by rock, explore the three main categories they fall into based on how they form.
Right, the big three.
And maybe get a peek at the cool tools scientists use to investigate them. We want clarity, less jargon, more relevance to, the ground beneath your feet.
Sounds like a plan.
So let's start right there. What exactly turns something the title of rock in the geological world?
Okay, well, the geological definition states that a rock is a coherent, naturally occurring solid consisting of an aggregate of minerals or, less commonly, a body of glass.
Okay, coherent, naturally occurring solid,
Yeah.
aggregate of minerals or glass. Let's break that down. Coherent.
Coherent means it holds together. You'd actually have to break it to separate its parts. Think of a big cliff face or maybe a statue carved from stone.
Ah, so it's solid. It sticks together.
Exactly. Its coherence is what lets it maintain its shape. It's not like, say, a pile of sand on a beach. That sand is made of mineral grains, sure, but it doesn't hold together on its own. It lacks that internal connection.
Right. Not coherent.
Got it.
And naturally occurring. That seems straightforward.
It mostly is. It just means geologists only count materials formed by natural geological processes. So things like concrete or bricks, even though they're solid and hold together.
They don't count because we made them.
Precisely. They're manufactured, not naturally formed by the earth.
Okay, natural and holds together. Now, an aggregate of minerals or a body of glass. This sounds like the ingredients list.
That's a good way to put it. The vast majority of rocks are aggregates, basically. Collections of mineral grains or crystals all packed together.
Grains or crystals, is there a difference?
Yeah, geologically there's a subtle one, though we might use the terms loosely sometimes. Think of a grain as just a small piece, could be a fragment of a mineral, a tiny chip off another rock, even a bit of natural glass. Sand grains are a perfect example.
Okay, little bits.
A crystal, though, is more specific. It's a single, continuous piece of a mineral that often has a distinct internal structure, and sometimes you can even see flat, geometric faces on the outside if it had room to grow.
Ah, like those quartz points you see.
Exactly like that. So some rocks are made of just one type of mineral crystal, all jumbled together. Others are a real mix of different mineral grains.
A mineral mosaic.
Kind of, yeah. And then, much less common, you have rocks that are essentially solid lumps of natural glass, like obsidian. That forms when volcanic lava cools down super fast.
Frozen lava, basically. Okay, so how do these grains or crystals actually stick together in most rocks? What's the glue?
Good question. There are two main ways. In what we call clastic rocks, the individual grains, think sand, silt, pebbles, are cemented together.
Cemented? Like with actual cement?
Well, natural cement. It's minerals that precipitate out of water that seeps through the spaces between the grains. Over time, these minerals grow and essentially glue the grains together. Sandstone is a classic example.
Okay, natural glue between the bits. What's the other way?
The other main type is crystalline rocks. Here, the mineral crystals themselves interlock directly as they grow. Imagine pieces of a 3D jigsaw puzzle fitting tightly together.
No glue needed, they just lock into each other?
Exactly. Granite is a good example of that, where you can often see the different interlocking crystals and those glassy rocks we mentioned. They're coherent either because they're one continuous glassy mass, or sometimes tiny glass shards get welded together when they're still really hot.
Clastic is cemented bits, crystalline is interlocking crystals.
Got it. Now, you mentioned rocks are basically chemicals. Does that mean all rocks have the same chemical recipe?
Oh, definitely not. It's like baking a chocolate cake has a very different recipe than, say, a lemon cake.
Right.
Same with rocks. Granite, for example, the stuff in countertops, is loaded with silicon and oxygen, plus aluminum, potassium, sodium. Those elements form minerals like quartz and feldspar.
Okay.
Now, compare that to marble, often used for statues, right? Its main ingredients are calcium, carbon, and oxygen, which mostly form the mineral calcite. Totally different chemical makeup.
Wow, completely different lists. Looking at the common elements in the Earth's crust, though, there's a lot of oxygen and silicon. There really is. And that's why the vast majority of rocks in the crust and mantle are made of silicate minerals, minerals built around silicon and oxygen.
Makes sense.
But what's also fascinating is that life plays a role, too, especially near the surface. Think about corals or shellfish.
They make shells.
Exactly. Out of carbonate minerals they pull from seawater. When they die, those shells pile up, get buried, and eventually can become carbonate rocks like limestone. A huge amount of the upper continental crust is actually made of this stuff.
So rock formation isn't just purely physical chemistry, life gets involved.
It certainly can. And while rocks made mostly of oxides, sulfides, or sulfates are less common overall, they're incredibly important. Economically, they're where we get many metal ores.
Interesting connection. Now, when we see rocks out in the world, sometimes they're loose like pebbles on a beach, but other times they're part of a huge cliff face. What's the distinction there?
That's the key difference between loose fragments and bedrock. Bedrock is the solid rock that's still physically attached to the Earth's crust underneath.
The main connected stuff.
Right. And when that bedrock is exposed at the surface, where we can actually see it and touch it, we call it an outcrop.
An outcrop.
Outcrops can be natural. Think of rounded hills, steep cliffs, riverbeds where water has cut down.
Yeah, you see those hiking.
Or they can be human-made. When we build roads, we make road cuts, we dig quarries, railway lines, foundations for buildings. Those all expose the underlying bedrock.
So that big wall of rock next to the highway is basically a man-made outcrop.
Exactly. It's an exposure of the bedrock that was previously hidden.
Right, because in a lot of places, like a forest or a city, the bedrock is covered up, isn't it?
Precisely. Soil, vegetation, sand, gravel, buildings, pavement, all sorts of things can cover the bedrock. But it's usually down there.
And it's important for building things, right?
Hugely important. For big structures like skyscrapers or bridges, engineers much prefer to anchor the foundations directly onto solid bedrock rather than building on looser soil or sediment. It's much more stable. So understanding where the bedrock is, how deep it is, what kind it is, that's critical for construction.
Makes total sense. Okay, so we've got a solid definition of rock now. But how did geologists even begin to organize this huge variety? You mentioned three main classes earlier. How did they figure that out?
Well, that's a fascinating bit of history. It takes us back to the late 18th century when geology was really just starting out as a science.
Okay.
People were looking at all these different rocks and thinking, wow, how do we make sense of this? They needed a system. One of the first big ideas came from Abraham Werner in Germany.
Werner. What was his idea?
He proposed that all rocks basically precipitated out of a giant primeval global ocean. In a specific order, too, he called them primary, secondary, and tertiary rocks. His followers were even called Neptunists.
Neptunists.
Yeah.
After Neptune, god of the sea. So everything came from water.
That was the idea. But it turned out to be a bit too simple. Around the same time, there was a Scottish doctor and farmer named James Hutton.
Hutton. I've heard that name.
Yeah. Father of modern geology, many call him. He took a totally different approach. He believed the present is the key to the past. He went out and looked closely at rocks.
Fieldwork.
Lots of it. He saw sand building up on beaches and thought, maybe rocks like sandstone form when sediments like this get stuck together.
Okay, logical.
He also saw rocks like granite that looked like they'd been molten and squeezed into older rocks. So he proposed they formed from cooling magma.
From heat inside the earth.
Exactly. And he noticed that the older rocks right next to these magma intrusions seemed altered, baked almost. He put that down to subterranean heat.
So he was observing processes and results.
Precisely. His ideas, championed by followers called Plutonists after Pluto, god of the underworld, because of the heat angle directly challenged Werner's Neptunists.
It's a scientific showdown. Neptunists versus Plutonists.
It really was. And eventually the evidence piled up in favor of the Plutonists. It became clear that some rocks definitely formed from molten material, and others formed from cemented sediments, and yet others were changed by heat and pressure.
So Hutton's ideas won out.
They did, and they formed the basis for how we classify rocks today, based on their origin, their genesis, how they were actually formed.
Okay, so that leads us to the three main classes. What are they?
Right. Building on Hutton's insights, we have igneous rocks, sedimentary rocks, and metamorphic rocks.
Igneous, sedimentary, metamorphic. Let's start with igneous.
Igneous rocks form from the cooling and solidification or freezing of molten rock.
Molten rock, like magma.
Exactly. Molten rock below the surface is called magma. If it erupts onto the surface, we call it lava. When either magma or lava cools and solidifies, you get igneous rock. Think of Hawaii Islands built almost entirely of cooled lava flows.
Rocks literally born from fire, or at least intense heat.
Okay, what about sedimentary?
Sedimentary rocks form in a couple of ways, both mostly near the Earth's surface. One way is by cementing together loose grains clasts that were broken off pre-existing rocks.
Like the sand Hutton saw. Just like that. Sand, mud, pebbles, even bits of shells. They get buried, compacted, and then cemented together by those natural mineral cements we talked about. Sandstone, shale, conglomerate, those are all clastic sedimentary rocks.
Okay, cemented fragments. What's the other way?
The other way is through precipitation. Minerals dissolved in water, like in lakes or oceans, can crystallize and settle out of the water, forming layers of chemical sedimentary rock. Rock salt and some types of limestone form this way.
So either cemented bits or precipitated crystals.
Got it.
That leaves metamorphic.
Metamorphic rocks are rocks that have changed. They start out as some other rock, could be igneous, sedimentary, or even another metamorphic rock, and then they get subjected to intense heat, pressure, or stress deep within the earth.
Changed, but how?
These conditions cause changes while the rock remains solid. This is key, it doesn't melt.
No melting involved.
Right. The heat and pressure can cause the minerals inside the rock to recrystallize, maybe grow larger, or even transform into completely new minerals. The texture can also change dramatically, sometimes forming layers or bands.
So they're like recycled rocks, transformed by extreme conditions underground.
That's a great way to think about it. And it's amazing how these three rock types link together and relate to different plate tectonic settings, like igneous rocks at mid-ocean ridges and volcanoes, sedimentary rocks on continental shelves, metamorphic rocks deep in mountain ranges. But that's a topic for another deep dive, perhaps.
Definitely. Okay, so within those three big families, igneous, sedimentary, metamorphic, there are still tons of different specific rock types. How do geologists tell those apart? What features do they look at?
Yeah, you're right. Each class has many members. We distinguish them based on several key physical characteristics. One is grain size and shape.
Size and shape of the bits inside.
Exactly. The grains, the mineral crystals or fragments, can range from too small to see without a microscope up to, well, boulder-sized in some cases. And a rock might have grains all roughly the same size or a real mix.
And shape matters too.
It does. Some grains are kind of roundish or blocky. We call those equant. Others are flattened or elongated, like plates or needles. We call those inequant.
Equant, like equal dimensions. Inequant, not equal.
You got it. And those inequant grains are particularly important in metamorphic rocks. Under pressure, they can all line up parallel to each other, creating a layered or banded look called foliation.
Ah, foliation. That layered look in some metamorphic rocks. Okay, so size and shape. What else?
Composition is crucial. What the rock is actually made of, the proportions of different chemical elements.
The recipe again?
The recipe, yeah. Which in turn dictates which minerals are present and how much of each. But remember, it's not just the chemical recipe.
Right, temperature and pressure matter too.
Exactly. Two rocks could have the exact same chemical ingredients but end up with different minerals if they formed under different TMP conditions.
Okay, composition is key. But context matters. What about texture? We mentioned that briefly with clastic and crystalline.
Texture is about how the grains are arranged and connected. How do they fit together? Are they interlocking like puzzle pieces? Are they just cemented together loosely? Are inequant grains aligned or randomly oriented? It's the overall fabric of the rock at a small scale.
The way the pieces are put together.
Precisely. It might sound a bit abstract, but it becomes really clear when you look at examples. Think of a granite with big, visible interlocking crystals versus a smooth, glassy obsidian. Very different textures.
Gotcha. And lastly, layering. Some rocks are obviously layered.
Yes, layering is another big one. Some rock formations show distinct layers. These can be due to changes in grain size or composition or texture or that alignment of grains we talked about, the foliation.
Tons of layering.
Yep. In sedimentary rocks, we call it bedding. Often reflects changes in what kind of sediment was being deposited, maybe a layer of sand, then a layer of mud, then more sand.
Like layers in a cake?
Sort of. And in metamorphic rocks, that alignment of minerals creates metamorphic foliation, which is also a type of layering. Think of schist or gneiss. They often look distinctly banded.
Okay, so grain size and shape, composition, texture, and layering. Those are the main clues geologists use to identify specific rocks, and each rock type gets a name. Where do those names even come from? Sound like there could be hundreds.
There are hundreds, and the names come from all over the place. Some are pretty straightforward, named after the main mineral, like quartzite is mostly quartz.
Makes sense.
Others are named after places where they were first found or are really common, like andesite, named after the Andes Mountains.
Ah, geographic names.
Yeah. Some names have roots in old legends or Latin or Greek words describing a feature, and some are just traditional names used by miners or quarry workers for ages. It's a real mix of history, geography, and description.
Fascinating. So we know what rocks are, how they're classified, but how do geologists actually study them? You can't just look at a cliff and know everything, right?
Chuckles. Well, you'd be surprised what an experienced eye can tell in the field. But no, the formal study starts with careful observation at an outcrop.
Back to the outcrop.
Back to the outcrop.
Yeah.
Geologists look at how different rock layers relate to each other, search for structures like folds or faults, note the color, estimate grain size if possible, check for layering, all recorded meticulously in a field notebook.
Document everything.
Absolutely. Then, usually, they'll use a geological hammer carefully, with eye protection, to break off a representative sample. A fist-sized piece, usually called a hand specimen.
To take back to the lab.
Exactly. But even right there in the field, a crucial tool is the hand lens.
The magnifying glass.
A small, powerful one, yeah. It lets you see sand-sized grains clearly, get a much better look at the texture, maybe even identify some common minerals right on the spot.
So field observation, sample collection, hand lens inspection. What's next in the lab?
For a really detailed look at the minerals and how they fit together, the gold standard is making a thin section.
Thin section. Sounds delicate.
It is. You take a small chip of the rock, glue it to a glass slide, and then use special saws and grinding powders to grind it down incredibly thin.
How thin?
About 0.03 millimeters,
Right.
thinner than a human hair.
Wow. Why so thin?
Because at that thickness, most mineral grains become transparent or translucent.
Ah, so light can pass through them.
Precisely. Then you put the slide under a petrographic microscope.
Not just any microscope.
Yeah. Nope. A petrographic microscope uses polarized light. Light passes through a special filter first, then through the thin section. As that polarized light interacts with the crystal structure of each mineral grain, it produces these amazing, vibrant interference colors.
Like stained glass.
Very much like stained glass.
Yeah.
And the specific colors, how they change when you rotate the microscope stage, they're diagnostic. They help you identify the minerals.
Incredible.
So with a thin section, you can identify most minerals, see exactly how they're interlocking or cemented, measure grain sizes accurately. It tells you so much about the rock's history. You can even take photos through the microscope photomicrographs to document it.
That reveals a whole hidden world. But technology marches on, right? Are there even higher tech ways to study rocks now?
Oh, absolutely. Since the mid-20th century, geologists have gained access to some incredibly powerful analytical instruments.
Like what?
Well, there are scanning electron microscopes, SEMs. They give you extremely high magnification images of rock surfaces, showing tiny textures you'd never see otherwise. They can even map where different chemical elements are concentrated.
Wow.
Then there are electron microprobes, which can zap a microscopic spot on a single mineral grain and tell you its exact chemical composition.
Super precise.
Very. Mass spectrometers let us measure isotopes, which is key for dating rocks or figuring out their origins. And X-ray diffractometers can identify minerals based on how their crystal structures scatter X-rays.
That's some serious kit. So this combination of fieldwork, hand lens, microscope, and these advanced machines.
Exactly. Each tool provides a different piece of the puzzle. The high-tech stuff gives incredibly detailed chemical and structural data, while the microscope shows the texture and mineral relationships, and the fieldwork provides the crucial context. It all works together.
To understand how the rock formed, where it came from.
And ultimately, to piece together the history of our planet. That's the goal.
It's amazing. Just looking at that photo of the students studying the sandstone outcrop, you can almost see them thinking about all this.
Right. They're looking at the layers, the bedding, maybe wondering how coarse the sand grains are, whether they're rounded or angular.
Trying to figure out if it was an ancient beach or sand dunes or a river.
Exactly. Using the rock's the grain size, sorting, layering to decipher its past environment, it all connects back.
Okay, so let's wrap up this deep dive. We've covered the geological definition of rock. Coherent, natural, solid, made of minerals or glass.
Check.
We hit the three main classes based on origin. igneous from cooling melt,
Sedimentary from cemented bits or precipitation.
and metamorphic from solid state change under heat and pressure.
Got him.
And we looked at the geologist's toolkit,
Yeah.
outcrop observation, hand lens, the amazing thin sections under the petrographic microscope.
And all the high-tech analytical gear like SEMS and microprobe.
Right. It all builds a picture.
It really does. Understanding rocks gives us such fundamental insights into Earth processes and history. Even the plainest looking rock is like a book holding chapters of our planet's past.
It definitely makes you look differently at the world around you.
Yeah.
So maybe a final thought for everyone listening. Next time you see some interesting rocks, maybe in a building, a garden wall, a cliff face, even just a pebble,
Yeah.
take a closer look. Think about what we've discussed. Is it crystalline or clastic? You see layers, any visible grains. What story might that rock be telling? What geological history is right there, waiting to be read?
A great challenge. And with that, I think we can confidently say we've covered the definition, the three main classes, and the study methods for rocks, hitting all the key points from our source material today.